Hello everyone, I'm Yazan Ibrahim, or as some of you might know me, Yazan Abu Ghosh. Today we're going to dive into a fascinating and essential topic. Welcome back to our ongoing exploration of AI operations. In our previous chapter, we discussed the critical aspects of supervising AI solutions once they are deployed. Today we're taking a crucial step back to look at how we ensure these solutions are fit for purpose before and during their operational life. This brings us to Chapter 10, Testing Techniques for AI Solutions. This chapter details the essential methods for validating and verifying AI models and the broader systems they inhabit. A key theme will be distinguishing between conventional software testing techniques that have been adapted for the unique context of AI and a growing suite of AI-specific testing methodologies. These specialized techniques address unique AI characteristics such as model performance, robustness against unexpected inputs, fairness and the mitigation of bias, the explainability of AI decisions, and security against novel adversarial attacks. This chapter emphasizes the absolute necessity for comprehensive testing strategies that rigorously cover data quality, model accuracy, ethical considerations, and operational reliability to ensure that AI solutions are not only effective but also safe, fair, and trustworthy. The principles of robust testing for AI systems are underscored by various governance and risk management frameworks. For instance, ISO IEC 42001, the standard for AI management systems, inherently requires verification and validation activities as part of the AI system lifecycle. The NIST AI Risk Management Framework, AI RMF, strongly advocates for measurement and testing to manage AI risks. Similarly, best practices from ISACA and the AAIA consistently highlight the importance of rigorous testing and validation in the governance of IT systems, principles that are even more critical when applied to complex and impactful AI solutions. So, let's delve into the world of ensuring our AI solutions are truly ready for the real world. Introduction to AI testing. Beyond traditional approaches. Testing AI solutions is a multifaceted endeavor that extends beyond the paradigms of traditional software testing. While AI systems often include conventional software components, their core, the AI model itself, is typically data-driven, can exhibit probabilistic behavior, and learns and evolves. This necessitates a specialized approach to validation. Are we building the right system? And verification. Are we building the system right? The goals of AI testing are to ensure the AI solution meets its specified functional and non-functional requirements, verify the accuracy, reliability, and robustness of the AI model, identify and mitigate biases and ensure fairness in AI outcomes, assess the security of the AI system against both traditional and AI-specific threats, confirm that the system operates ethically and in compliance with relevant regulations, ultimately build confidence and trust among stakeholders that the AI solution is fit for its intended purpose. A comprehensive testing strategy for AI must cover the entire life cycle from data inputs and model development to deployed system behavior and ongoing operational reliability. This holistic approach is vital for managing the unique risks associated with AI, a concept central to frameworks like ISO IEC 23894 on AI risk management. Distinguishing AI testing types broadly, testing techniques for AI solutions can be categorized into two main groups: conventional software testing techniques adapted for AI. These are established software testing methods that are applied to the non-AI components of an AI system, as well as to the AI model when treated as a software component with inputs and outputs. AI-specific testing techniques. These are specialized methods designed to address the unique characteristics of AI models, such as their learning behavior, data dependency, decision-making processes, ethical implications, and vulnerabilities. Let's explore each of these in more detail. This distinction is also recognized in Domain 2, Section E of the IIP framework. Conventional software testing techniques applied to AI solutions. Many well-established software testing techniques remain essential when testing AI solutions. These techniques primarily focus on the traditional software components that surround or support the AI model, the integration points between different parts of the system, and the overall application's functionality, performance, and security. In some instances, the AI model itself can be treated as a component, and these conventional tests are applied to its inputs and outputs. Leading practices from ISACA on IT auditing and control often emphasize the importance of these foundational testing methods. Unit testing, conventional focus, testing individual isolated software components or modules, e.g. functions, classes, to verify that each unit performs its specific task correctly. AI application, testing data preprocessing functions such as modules for data cleaning, transformation, normalization, or feature engineering. Validating utility functions used in the AI pipeline, API integration components, and modules responsible for data ingestion or output formatting. For some simpler or more transparent AI models, it might be possible to unit test individual functions within the model's codebase, such as specific algorithmic steps or activation functions, if accessible, ensuring that the user interface components responsible for displaying AI results or modules handling user input for the AI function as expected. Integration testing conventional focus. Testing the interfaces and interactions between different software modules, components, or systems to ensure they work together correctly and data flows accurately between them. AI application testing the integration of the AI model, often served as an API, with the larger application or system it's part of. This ensures that data is correctly passed to the model and that the model's predictions or outputs are correctly received and processed by the calling application. Verifying the interactions between various components of the MLOps pipeline, such as data ingestion pipelines, the AI model training and serving infrastructure, and downstream systems or user interfaces that consume the AI's output. Ensuring that APIs serving AI model predictions handle requests, responses, authentication, and error conditions correctly and efficiently. System testing conventional focus. Testing the complete integrated software system as a whole to verify that it meets all specified functional and non-functional requirements from end to end. AI application, evaluating the end-to-end functionality of the entire AI-powered application, including all user workflows that involve or rely on AI-driven features or decisions, verifying that the complete AI system delivers on the business objectives and requirements defined during the problem definition and scoping phase, testing against non-functional requirements such as response time for AI predictions, overall system throughput, reliability under load, and usability of AI-enhanced features. User acceptance testing, UAT, conventional focus, testing conducted by end users, clients, or business stakeholders to validate that the software system meets their specific needs, expectations, and business requirements in a real-world or simulated operational environment before final deployment. AI application, having intended end users interact with the AI system to ensure its outputs, predictions, recommendations, classifications are useful, understandable, relevant, and effectively solve their business problems. Gathering critical user feedback on the AI's performance in practical scenarios, its usability, the clarity of its outputs, and the overall level of trust it inspires. Verifying that the AI solution from the user's perspective genuinely addresses the intended problem and integrates well into their existing workflows. Performance testing, including load and stress testing. Conventional focus, evaluating the responsiveness, stability, speed, scalability, and resource consumption of the software under various anticipated and peak load conditions. AI application, measuring the inference speed, latency of the AI model, how quickly it can generate a prediction after receiving an input. Assessing the throughput of the AI system, the number of predictions or transactions it can handle per unit of time, e.g. queries per second. Load testing, evaluating system performance under expected peak loads to ensure it remains stable and responsive. Stress testing, pushing the system beyond its normal operating limits to determine its breaking point and how it handles extreme conditions. Evaluating the resource utilization, CPU, memory, GPU, network bandwidth of the AI model during training and inference, and of the supporting infrastructure to identify bottlenecks and optimize efficiency. Testing the performance and scalability of data pipelines that feed data into the AI model, as these can often be performance bottlenecks. Security testing, conventional aspects. Conventional focus, identifying and mitigating security vulnerabilities in the software application, its data, and its infrastructure through techniques like vulnerability scanning, penetration testing, and secure code review. AI application, testing for common software vulnerabilities, e.g. SQL injection, cross-site scripting or XSS, insecure authorization in the application components that surround or interact with the AI model, securing APIs that expose AI model functionalities, ensuring proper authentication, authorization, and protection against common API attacks, protecting the underlying infrastructure where AI models are hosted and data is stored using traditional network and server security best practices. It's important to note that AI-specific security threats like adversarial attacks or data poisoning require specialized AI testing techniques, which we will discuss shortly. These conventional testing methods provide a crucial baseline for ensuring the overall quality and reliability of AI-powered systems. However, they often need adaptation for AI nuances, such as managing complex test datasets, dealing with non-deterministic outputs, and defining appropriate test oracles. AI-specific testing techniques. While conventional software testing techniques are essential, they are insufficient on their own to address the unique challenges and risks posed by AI systems. AI-specific testing techniques are designed to evaluate the core AI model's learning behavior, its dependency on data, its decision-making processes, and its ethical implications. These techniques delve deeper than just functional correctness. Model performance and accuracy testing beyond basic metrics. Focus, evaluating how effectively the AI model accomplishes its intended task, e.g., classification, regression, generation, using a range of metrics relevant to the specific AI paradigm and business context. Techniques. Offline evaluation. This is the most common approach where the trained model is tested on a holdout test dataset, data that was not used during training or validation. Performance is measured using appropriate metrics for classification tasks, accuracy, precision, recall, sensitivity, F1 score, area under the ROC curve, AUC ROC, area under the precision recall curve, AUC PR, confusion matrix analysis. For regression tasks, mean absolute error, MAE, root mean squared error, RMSE, R squared. For language models, perplexity, blue score. For translation, rouge score. For summarization. Slice-based evaluation. Going beyond aggregate metrics, this involves analyzing model performance on specific critical subsets or slices of data. For instance, evaluating a medical diagnosis AI separately for different age groups, genders, or ethnicities to identify areas where the model underperforms or exhibits disparities. This is crucial for fairness assessments, confidence scoring and calibration, evaluating the model's own confidence scores for its predictions. A well-calibrated model's confidence should correlate with its actual accuracy, e.g., if it's 90% confident, it should be correct about 90% of the time. Benchmarking, comparing the AI model's performance against established benchmarks, baseline models, e.g., simpler models or existing solutions, or state-of-the-art results for similar tasks to understand its relative performance. Robustness testing focus, assessing how well the AI model maintains its performance and stability when faced with noisy inputs, slightly perturbed data, unexpected inputs, or minor variations in the input data distribution that it might encounter in the real world. A robust model should not fail catastrophically or produce wildly incorrect outputs due to small realistic deviations in input. This is a key characteristic of trustworthy AI as highlighted by ISO IEC TR 24028. Techniques. Input perturbation, introducing small, often imperceptible changes to the input data, e.g., adding random Gaussian noise to images, slightly altering pixel values, making minor typographical changes to text, slightly modifying numerical values in structured data, and then observing the stability and correctness of the model's output. Adversarial testing for robustness. This involves intentionally crafting inputs known as adversarial examples that are designed to deceive or mislead the AI model into making incorrect predictions, even if the changes made to the input are minor and often unnoticeable to humans. This tests the model's vulnerability to such manipulations. Testing with out-of-distribution (OOD) data, evaluating how the model behaves when it encounters data that is significantly different from the data distribution it was trained on. A robust model should ideally indicate low confidence for such inputs, flag them as OOD, or default to a safe mode rather than making spurious high-confidence predictions. Stress testing with edge cases and boundary conditions, systematically subjecting the model to extreme values, rare combinations of inputs, or boundary condition inputs that might push the model beyond its normal operating parameters to observe its handling of these challenging scenarios. Fairness and bias testing focus, proactively identifying, measuring, and quantifying unfair biases in AI model behavior and outcomes across different demographic groups or individuals with legally protected characteristics, e.g., race, gender, age, religion, disability. The goal is to ensure equitable treatment and avoid discriminatory impacts. This is a critical ethical consideration strongly emphasized by the NIST AI, RMF, and various AI ethics guidelines. Techniques, bias metrics, quantification utilizing various quantitative fairness metrics to measure disparities in model performance or predictions across defined subgroups. Common metrics include demographic parity, statistical parity, ensures the proportion of individuals receiving a positive outcome is similar across groups. Equalized odds ensures true positive rates and false positive rates are similar across groups. Equal opportunity ensures true positive rates are similar across groups, often for desirable outcomes. Predictive rate parity ensures positive predictive value precision is similar across groups. Subgroup performance analysis, comparing key model accuracy metrics, e.g. true positive rates, false positive rates, error rates, specifically for different defined demographic groups to identify any significant performance disparities. Counterfactual fairness testing. This involves evaluating if changing a sensitive attribute, e.g. gender in a loan application, while keeping all other relevant features constant would alter the AI model's prediction or outcome. Such a change might indicate individual-level bias. Intersectionality testing. Moving beyond analyzing bias along single attributes, like race or gender in isolation, to assess for biases that may occur at the intersections of multiple attributes, e.g., specific biases against women of a particular ethnicity or older individuals from a certain region. Explainability and interpretability testing and XAI testing. Focus: evaluating the extent to which an AI model's decision-making process and its outputs can be understood by humans. This is crucial for building trust, enabling debugging, ensuring accountability, and meeting regulatory demands for transparency, a principle often cited by ISO and ISACA. Techniques: feature importance analysis, utilizing techniques like Shapley additive explanations, or LIME, local interpretable model agnostic explanations, to understand which input features had the most significant influence on a particular prediction made by the AI model. Rule extraction: for certain types of models, like decision trees or some ensemble methods, attempting to extract human understandable rules or decision paths that approximate the model's decision logic. Example-based explanations: identifying specific instances from the training data that are most similar or influential to a given prediction, helping users understand the decision by analogy. Testing the coherence, fidelity, and usefulness of explanations. Ensuring that the explanations provided by XI methods are not only generated but are also accurate representations of the model's actual behavior. Fidelity: are understandable to the target audience, e.g., developers, domain experts, end users, auditors, and are genuinely useful for their intended purpose, e.g., debugging, building trust, challenging a decision. Security testing for AI-specific vulnerabilities. Focus: identifying and mitigating security risks that are unique to AI systems, going beyond conventional software security testing. This directly addresses many of the concerns raised in Chapter 11, Threats and Vulnerabilities Specific to AI. NIST provides significant guidance on securing AI systems. Techniques: data poisoning attack simulation, testing the model's resilience against maliciously manipulated training data that is intentionally designed to compromise the model's integrity, introduce backdoors, or degrade its performance on specific tasks. Model evasion attack simulation, adversarial testing for security, as mentioned under robustness, but with a specific security focus on an attacker's intent to deceive the model during inference time. Model stealing extraction attack simulation, attempting to replicate or reverse engineer a proprietary AI model, perhaps by repeatedly querying its API and observing outputs to test the effectiveness of defenses against such IP theft. Membership inference attack simulation, testing whether an attacker can determine if a specific individual's data record was part of the AI model's training set by analyzing the model's predictions and confidence scores. This has significant privacy implications. Privacy attack simulation, e.g., model inversion, testing for vulnerabilities that could lead to the leakage of sensitive information from the model's parameters or its outputs, potentially reconstructing parts of the training data. Data quality and integrity testing for AI focus, ensuring the quality, integrity, appropriateness, and representativeness of the data used for training, validating, and testing AI models, as data issues are a primary cause of AI failures and biases. This links directly to the data management principles in Chapter 6. ISO IEC 42001 also places strong emphasis on data quality documentation and processes. Techniques: training data validation, rigorously checking training data sets for biases, errors, inconsistencies, missing values, and ensuring proper labeling accuracy and consistency. Test data adequacy and representativeness, ensuring that the test data set is sufficiently diverse, covers a wide range of expected and unexpected scenarios, is truly independent of the training data, and provides an unbiased measure of the model's ability to generalize. Data provenance and lineage testing, verifying the origin, history, and transformation trail of data to ensure its reliability, auditability, and to understand any potential embedded biases or quality issues from its source. Concept drift and data drift detection testing. While also a monitoring activity, this involves testing the effectiveness of mechanisms designed to detect if the statistical properties of the input data, data drift, or the underlying relationships between inputs and outputs, concept drift, have changed over time. Early detection is crucial before significant performance degradation occurs. These AI-specific testing techniques are often iterative and deeply integrated with the MLOps, machine learning operations lifecycle. They require specialized skills, tools, and a testing mindset that acknowledges the probabilistic, adaptive, and often complex nature of AI systems. Need for comprehensive testing strategies given the multifaceted nature of AI systems and the diverse range of potential issues from technical errors to ethical breaches. A comprehensive testing strategy is not just recommended, it's essential. Such a strategy must cover the entire AI lifecycle. Testing should not be a single phase at the end of development. It must be integrated throughout the AI SDLC from data acquisition and preparation, Chapter 6 and 7.1, to model training, validation, deployment, and ongoing monitoring, Chapter 9. Address multiple dimensions. The strategy must encompass data quality, ensuring the integrity, accuracy, and representativeness of data, model accuracy and performance, verifying that the model meets its functional objectives reliably, ethical considerations, proactively testing for fairness, bias, and transparency, operational reliability and robustness, ensuring the system performs well under real-world conditions and stress, security, protecting against both conventional and AI-specific threats. Employ a risk-based approach. Testing efforts and resources should be prioritized based on the potential impact and likelihood of risks associated with the specific AI application. High-risk AI systems, such as those defined by the EU AI Act or internal risk assessments guided by frameworks like ISO IEC 23894, will require more extensive and rigorous testing. Combine conventional and AI-specific techniques. Leverage the strengths of both traditional software testing methods and specialized AI testing techniques for holistic coverage. Involve multidisciplinary teams. Effective AI testing often requires collaboration between software testers, data scientists, ML engineers, domain experts, ethicists, and security professionals. Ensuring AI solutions are fit for purpose requires this diligent, multifaceted, and ongoing testing effort. It is a cornerstone of building trustworthy AI that organizations and society can rely on. Thank you for watching, and as always, continue learning, stay curious, and we'll see you next video.